All right, so let's go ahead with the robot dynamics. So till now we have seen how we basically deal with kinematics of robots. We are concerned with the motions and the relation between the end effector and the joint space, or in the forward kinematics where we are looking at how basically the end effector is actually placed as per the given joint angles for different configuration of robots. So that's what we have actually looked at in kinematics. So we did not really worry about the forces that are actually required to make robot move according to that trajectory. And we have seen also statics where robot is supposed to be stationary doing a particular task where it doesn't really move faster. So it is like a quasi-static or a static case where a robot is actually applying a force or a moment on a particular object or on a particular surface. So in those cases we have seen how we can basically analyze the robot for the required torque at the joints for applying a particular force at the end effector. So those things were taken by we had considered links as free body in their free body diagrams, and we had done the force and moment balance to find out the torques required at the particular joints for a particular amount of force to be applied at the end effector. Now we look at one of the major areas of robotics where basically we assume actually the robot actually moves an object or does a pick and place kind of an operation, or does a continuous operation where the robot is supposed to move faster. So in all those cases the dynamic effects come into place. And robot dynamics generally we say where we are actually in this case determining the forces and the torques required to cause a particular motion of the robot links. So obviously the motion is time varying, so we have position, velocity and acceleration profiles of the joints, and accordingly we are supposed to find out the torque profiles at each joint. So that is what is actually dynamics is concerned with. Now let's look at some of the examples. So robots are supposed to be, doing dynamic tasks also, which involve robot picking and placing an object in a particular amount of time, being very quick in these operations. So in all these cases, we have seen robots actually are supposed to do a task which could be very quick, which could involve the joints to move at a particular position profile, which involves the velocity and the acceleration also. So in particular dynamics is actually determination of forces and torques required to cause a particular motion of robot links, where the motion is generally in the form of joint or end effector trajectories. So obviously trajectories would mean the profiles of joints or the profile of the end effector in terms of position, velocity and acceleration. So obviously inertial effects come into play and are actually very important in dynamics. So which would also mean that acceleration analysis has to be done. We had seen in previous lectures the velocity analysis and the position analysis. So acceleration analysis would be required in this case. And we have gravity also playing a very important role. So there could be planar cases where gravity doesn't really affect, but in the most general case gravity has to be taken into the analysis. So gravity will have its impact. We have also left out the gravity in the static case, but now it could be included. Friction at the joints is also very important. Now robots, apart from other kind of rigid bodies, are actually multi-body systems or articulated bodies. They're connected bodies. So each body has an impact, each body's motion has an impact on the other body. So there are coupled effects, like coupled physical effects in terms of we have mass matrices, we have inertia tensors, we have centrifugal and Coriolis acceleration in this. So the knowledge of dynamics is actually very essential, because we finally would like to control these robots which are moving faster, which are doing a particular task. We want it to be done in a very precise manner with the least error. So in that case we need to control these robots, and for controlling we need to know about the dynamics of these robots. So all these get embedded actually into the dynamic equation of robots. Now, two aspects of dynamic analysis are generally looked at into. One is inverse dynamics, another is forward dynamics. So, inverse dynamics, we mean given the joint trajectories, that means given the position, velocity, and acceleration profiles of each joint of a robot, we need to determine the forces that are required to achieve them. We need to determine the torque profiles required to achieve such joint trajectories. And this is particularly important in the control of robotic manipulators. So to control a robotic manipulator, we need to apply a specific torque to those joints, and then we can basically achieve those trajectories. So it's very important in the control of robotic manipulators. And then the other aspect is forward dynamics, which is actually more concerned with the simulation of robots. So this is also a growing field, a contemporary field, where we assume some forces are acting, or the torque profile is acting at the joints. How would actually robot behave? What will be its joint trajectories? We can basically simulate them beforehand, actually, without even constructing these robots. And obviously, for all these things, we need the equation of motion, that is dynamic modeling, so which can be done by Newton-Euler methods, which is nothing but the elementary dynamics, which is a force, moment balance. And then we can also use Euler-Lagrange method, or the Lagrange method, which is more of an energy-based method. So in this class, we will be more concerned with the Lagrange method only. We will skip the Newton-Euler, though it's very elementary. Now, let's talk about basic dynamics. Suppose we have a spring mass damper system. So suppose we have a body of mass m, and then let's say it's connected to a rigid surface with some spring and a damper. So this goes back to the elementary dynamics, or you can say vibration course, where we have a spring and a damper with damping coefficient c and spring constant k. And suppose this is moving with some, and then some force is being applied to it, forcing function. So if we want to write the equation of motion of this kind of a block, so it's a rigid body with some constraints, so, and with some forcing functions. So the equation of motion of this kind of body, we can basically draw a free body diagram and balance the forces on both the sides. So in short, we get something like this: mx double dot, or you may even write with t, plus cx dot plus kx of t is equal to f of t. So this is what we typically write down, a second order equation of motion for a spring mass damper system. In this case, if we are actually given the trajectory, like if we are given the position profile with respect to time, so in terms of, suppose maybe x final t minus x naught t upon the total time, something like this. We have trajectories that we define into sine of pi t, any such function, any nonlinear function, or any other function if you are given. So obviously, because this is again a function of the time, so we can always find out the velocity profile with respect to this, and then we can also find out the acceleration profile. So for a given mass m and a given spring and damper coefficient c and k, we can basically estimate the force required actually to move the spring mass system with a trajectory like this. So force is determined for given trajectory. So this is, in robotics we call this specifically as inverse dynamics, ID. And if we are given the force f of t, if it is specified as a forcing function, maybe again a function of sine or cosine or any other function, and we are supposed to find out the trajectory x of t, x dot t, etc. So this is actually known as forward dynamics or simulation. Now this is a very simple case where we have a single body or a rigid body, and then it's moving. So it's very simple. We have a simple mass, which is scalar function, and then we have c and k. so they are generally a constant in this case. So we don't have those parameters varying, just the trajectories that are varying. So we can basically do this very simply. But in robotics, we generally have systems that rotate. One thing is that, so we have inertia, moment of inertia that comes into place. And then second thing is, in robotics we have multi bodies, and bodies are connected by joints. So the impact of each body on the other body is significant. We cannot just take them to be very simple or non-trivial, so they have to be analyzed properly. All right, so this is a single link robot, which can be also considered to be as a pendulum system. So this let's say is supposed to rotate as per along the axis, z axis. So obviously it has some mass, and obviously it has some associated inertia, moment of inertia, so about the axis, about the center of mass. Now if we want to write the equation of motion of this, so we can simply write it maybe this way: I theta double dot plus, or we can initially write it equal to tau. So this is a basic equation of motion of a pendulum rotating about a fixed axis. And obviously we assume here that there is no gravity, there is no friction, there is no other effects. So obviously this will be a very simple equation of motion for this pendulum. But because we do not generally we cannot ignore gravity, because pendulum is supposed to fall freely or maybe under the gravity. Though we could have single link systems where the robots do not act under the gravity, it could be a planar case. But in this case, let's assume there is a gravity component, so it will be I theta double dot plus something like this, mgl cos theta or something like this is equal to tau. So which means, so the gravity component has been taken into in the equation. And there could be other effects like friction at the joint, so we may add maybe c theta dot also in this case. But in general, this is the dynamic equation of the single link robot. So obviously I here can be replaced by ml square by, it could be ml square by 3, because it's about the axis of the robot. About the center of mass, we may have ml square by 12. So ml square by 3 theta double dot plus mgl, I have to see it's cos theta or sin theta, is equal to tau. So the torque required as per the given trajectory, if we are given some trajectory of theta and theta dot and theta double dot, if we are given a trajectory, we can easily find out the torque required for this pendulum. So we can basically so this is our dynamic model, or this is the equation of motion of the pendulum. Now with these equations, obviously we can control this single link manipulator to act as per our requirements in terms of performance, control performance and all, because we have the dynamic model with us. All right, so now in rotary systems, obviously we have seen that there is a moment of inertia component that comes into play. So it's not just the mass, as in linear systems we have the moment of inertia, which is very significant. Now in typical serial chain manipulators, so we have not just the one link, but there's another link that is connected, there is another link, and it's all a set of n links connected together. So it could be like, we may say this is link number 1, this is link number 2, this is link number I, and this is link number n. Each link obviously has its associated dynamics with it, and in a multi-body system, actually each link has an impact on the motion of the other link. So if we see a single link itself, so a single link can be visualized like this. So it can be said to be under the basically influence of some linear velocity. It has some angular velocity. It is under the influence of a force and under the influence of a moment. So obviously we can maybe write it this way, as we have seen earlier also. So this is V I in I omega I. So obviously each link has its linear velocity, maybe at the, let's say, link origin, or maybe at the center of mass, and each link obviously has an associated angular velocity, and each link is actually influenced by the forces and the moments. So we can basically do analysis in terms of Newton Euler, where basically we try to do this force and moment balance, and try to propagate the velocities to actually from link 1 to link n, and accordingly link n will have some linear and angular velocity, and then we can do something called as force balance and moment balance, so whereby we can basically find out the torque required at the joints for a particular trajectory. In the energy based methods, actually we are basically again interested in the energy of each link, and we can basically sum them together. So obviously energy would involve knowing of, or the knowledge of, these velocities, angular velocities and the linear velocities. So the dynamic equation of motion basically looks like this, which is also called as state space equation of the robots, because here the states generally in the form of theta and theta dot are actually here embedded here. So let's say these are functions of these states, so that's why this is also called a state space equation, or we can simply call it as a structured a dynamic equation of motion, where tau represents the torque vector, so tau 1, tau 2, tau 3 as per the number of links or the number of actuators, and then we have theta double dot, which is nothing but the vector of joint accelerations, and the theta dot is vector of joint velocities, theta is the vector of joint positions, and capital M actually includes the mass matrix of the manipulator, and V represents the vector of centrifugal and Coriolis components. So obviously these are centrifugal forces that act on each link, and the Coriolis component of acceleration that is associated with the links. G represents the vector of gravity terms. So obviously every link in a general case is under the influence of gravity, so obviously we'll have gravity components, and all these together actually would lead us to the torque required for the particular trajectory. Now this can also be represented in an analogous way, where we have tau is equal to I theta double dot plus h plus gamma, where actually h can be is nothing but a different representation for this Coriolis and centrifugal components, and gamma is here to replace actually g, so nothing different, and I represents actually the mass matrix of the manipulator, or we can say it is also called as the inertia tensor of the manipulator. Now the Lagrangian formulation is based upon the energy I can say energy method. So here we define the kinetic energy of a manipulator's ith link, which is the ith link which is subjected to, which has some linear velocity and also angular velocity. So this is how we basically represent the kinetic energy of an ith link or an ith body, which has some linear velocity about the center of mass, which is vci, and mi is the mass of the link, and omega I represents the angular velocity of the link about its mass center, and ici here would refer to the moment of inertia of the ith link about its mass center. So this is how we can basically represent kinetic energy of an ith link, and then we can sum all these kinetic energies for the whole manipulator to be ki summation ki I is equal to 1 to n. So it's very important to know that we should know the mass of the each link, and we should also know the velocity of the center of mass of the links, and also the angular velocity of the links should be known, and also the moment of inertia about the center of mass should be known. So if we know all these things clearly, we can evaluate kinetic energy of the links, and we can sum them for the kinetic energy of the whole manipulator, which can be put up in the quadratic form because of this being vectors and the capital M being the matrices. So for the whole manipulator we can basically put it up this way. Similarly, we have potential energy of the link, which can be written as mgh, where h here refers to the position vector of the center of mass of the link from the origin or from the base frame, and this is the gravity vector in the base frame. So this is the moment in the potential energy. This uref to keep that the potential energy always remains positive, though it can, it finally goes to zero because of the partial differential that we'll be using further. So total potential energy can be again a summation of all these potential energy of each link, which would include mass of the each link and obviously the position vector of each link. G will be constant. Now the Lagrangian is defined as the difference between kinetic energy and the potential energy, the whole manipulator. This is how we define capital L, that is the Lagrangian, and this is the differential equation that we basically use to find out the equation of motion. So rate of change of Lagrangian with respect to the partial derivative of Lagrangian with respect to the theta dot minus partial derivative of Lagrangian with respect to theta gives us basically the torque associated with the manipulator. So we can put L is equal to K minus U and then do some manipulation here. So we'll get something like this, and this equation actually, after doing all these calculations, will lead us to something like this, which was actually the dynamic equation of the robot.